Hello everyone, and welcome to today's webinar, When Less is More, Reducing Dose, Damage, and Duration with Counted EELS. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speaker at the end of the presentation. If we don't get to your question, we'll follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Liam Spillane has been working in the field of electron microscopy for the past 18 years. He started his career as a PhD student at Imperial College London, studying oxide thin films using aberration-corrected STEM and monochromated EELS. After completing his PhD, he worked as a postdoctoral research assistant in advanced electron microscopy, working on the structural and chemical characterization of materials across a number of projects, including nanoparticle toxicology, ferroelectrics, nanoparticle catalysts, and solid oxide fuel cells. After leaving Imperial College in 2012, Dr. Spillane joined Gatan, initially working with the UK Sales and Service Group for a number of years. He relocated to Gatan, USA in Pleasanton, California in 2018, where he is currently the application scientist for Gatan's STEM, EELS, and GIFT products. Now over to Liam.
Thanks, Jonathan. And yeah, thanks everyone for attending the webinar, When Less is More, Reducing Dose, Damage, and Duration with Counted EELS. So before we get started, I'd just like to give some acknowledgements and thanks to everybody who was involved. So there's a lot of experiments that I show, and I'm obviously not the sole person who does those. So thanks to the Gatan product and software team. And then thanks in particular to Berit Guge, who's based at the Max Planck Institute for Chemical Physics in Dresden, for providing some of the great samples that I'll be showing in the presentation today. Okay, so let's get started. So how do we begin? So let's start thinking about EELS detection challenges. So EELS is challenging to detect. Why is that? So there are features from very, very small energy, so from milli-eV all the way up to keV energy. So we have to go over a very, very large energy range. We also need really, really high energy resolution. So the features that, in the kind of the phonon, the milli-eV range need kind of very, very tight energy resolution. So like tens of milli-eV, as opposed to things that are much higher energies that, need a few EV or tens of EV to resolve. We also have a very, very large range of feature intensities. So some things are very, very faint. Some things are extremely bright and intense. And that gives us this problem with dynamic range. So we need a really, really, really large dynamic range to look at the full energy loss spectrum. So I've just simulated a spectrum to kind of give you kind of that in kind of real money. So what we're looking at here is a spectrum that was simulated using EELS Advisor in digital micrograph. And it's some kind of just kind of fictional oxide. So 40% oxygen, and then a mix of molybdenum, iron, and cobalt. So 20% by weight of each of those cations. And the simulation is up to 20 keV, so like really, really high energy loss. So I'm going to step through the spectrum now, and we can kind of take a look at the various features in our energy loss spectrum. So the first thing, which is always the brightest, is our zero loss peak. So in this particular spectrum, the zero loss peak intensity is of the order 6 × 10 to the 10 count, so super, super high. Next feature is our bulk plasmon, and that in this spectrum is 2 × 10 to the 9 count. So the plasmon sits around 20 or 30 EV, right? So not high energy loss, but you can see we've already kind of lost one order of magnitude just going from 0 to a few tens of EV. What next? Okay, so we take a look at our oxygen K edge. We're down to 1 × 10 to the 7 count, so 3 orders of magnitude decrease, and we're only at 500 EV, 530 EV. iron L23, drop again, and then cobalt L23. So you can kind of see the trend. We have this really steep drop in intensity. So our like transition metal L edges at 700 EV, we're down to 10 to the 6 counts. If we go to a couple of thousand EV, we drop more orders of magnitude. So we're down to like 10,000 counts in our molybdenum L. And then if we start going out to transition metal K edges, then the problem becomes kind of more stark. So iron K, we're at kind of 3,000 counts. Cobalt K, same sort of order of magnitude. And then the last feature in this spectrum is our molybdenum K edge, which is like down at 10 to the 2 counts. So 9 times 10 to the plus 2. So the difference between 0 and 20 keV, we're looking at like 8 orders of magnitude. So this is a massive number. Kind of just on this note, yeah, so this is actually something that you can target if you have the right setup. So this is some really nice work that my colleague Andrew has done in the last year or so. So Andrew actually did some mapping of transition metal K edges. So iron K, manganese K, and cobalt K. And you can see from this data that really nice, Andrew was actually able to map manganese precipitates in this kind of iron cobalt oxide matrix. If anyone is interested in this particular project, the QR code for this e-brief is here to the left. And just one thing I kind of wanted to say is this was done on what some people would consider a workhorse microscope. So a Joel F200, no like kind of next gen like R&D stuff. It's just a standard uncorrected microscope. And we used a GIF Continuum with the stellar camera and counting EELS. So this is not like a unique thing for like certain vendors. This can be done on a Joel microscope. It can be done on other microscopes. The key is that the acquisition time is going to be really long and the current's going to be quite high. So this is something that's interesting to do, but doesn't suit all samples, for example. Bear in mind, this is the work that was done with the iron and the cobalt K edges. If you wanted to do something higher at the molybdenum K edge, there's 33x less signal over here than there is here, right? So we're already at a very high dose at 8,000 EV. We need even higher dose at 20 keV. So the stuff that we're going to be able to do out here is going to be limited. Okay, so I kind of went off on a little tangent there talking about high energy loss EELS, but kind of the take home here is like we have these signals that are super bright, super faint, and we kind of want access to all of these signals. So this is a big detection challenge, and how can we get around this? So in an ideal world, if we had a perfect detector, it would allow us to capture all of our data in one go, so a single shot. What would be required for us to do that? So we would have to have an infinite or an unrealistically large number of pixels, because it's the pixels which essentially define our sampling resolution. So that's kind of a resolution argument there. If we want high resolution over a large range, we need like lots and lots of very small pixels. We also would require an infinite or a high enough dynamic range in the single detector. So you see that we needed like 8 orders of magnitude in that spectrum I just showed you. So our detector would need to be able to deal with that. And it would also have to have 0 like readout noise. So we would kind of want a noise-free detector with infinite dynamic range and an infinite number of pixels. Now, we live in the real world and we're based in kind of, reality. So our data needs to be acquired with a real world physical detector. So it has a finite number of pixels. So that's going to give us a finite digital sampling resolution. And it will have a finite dynamic range. So we're not going to be able to acquire all of our signals in a single shot, most likely. Okay, so we're talking about detector limitations, how can we get around some of the limitations of our detector? So the primary ones, in terms of a counting detector, are the first two bullets here. So finite number of pixels, finite dynamic range, because fortunately a counting camera has near zero readout noise. So we can kind of cross out the third one just by using counting cameras. But we're still, we still can't get around these just purely in terms of the detector. So what has been a thing to do for some time is to compromise, and instead of acquiring one spectrum, we acquire two, and that's using a technique called dual EELS. That allows us to do a couple of things that are really, really helpful. So we extend the effective energy range at a given energy resolution. What does that mean? So essentially, if we have two spectra at the same effective magnification, we're just doubling the number of pixels we have in our kind of end result at the same dispersion. So we double the energy range whilst keeping the resolution the same. That can be quite useful. It also allows us to extend the effective dynamic range, and that's because we can have variable exposure. Okay, so we have two spectra that we're acquiring. They can have different exposure times, and this really is kind of a massive benefit when we're trying to deal with the huge dynamic range that we're trying to acquire in the EELS spectrum. And this is kind of a bread and butter technique that has been used for a long time. Now, why is this a compromise? Okay, so this doesn't come for free. It's a compromise because it takes longer. If we're acquiring two spectra instead of one, then it's going to take longer. Okay, so it's net slower. It's also dose inefficient to expose the sample and only acquire part of the spectrum. Okay, so we're basically giving the sample more dose and we're not getting all of the signal at the same time. Okay, so this is kind of the how, like the what is dual EELS. Okay, so it's essentially near simultaneous acquisition of a low loss and a high loss spectrum with different exposure times. So these names, low loss and high loss, are somewhat arbitrary. So you can do like a zero loss and a low loss spectrum and a core loss, but you can also do like double core loss, okay? But the most common thing is to acquire the zero loss, the low loss information in one spectrum, and your core loss information in the higher of those two. Why? Okay, so the low loss data and the ZLP allow like kind of full or more complete processing of the high loss data. So you can do things like deconvolution, absolute thickness mapping, full quantification, areal density maps, for example, volumetric density, plural scattering correction. So all of these really nice things require the low loss information, okay? And it has been for some time that dual EELS is the technique that gives us easy access to both of these kind of parts of the spectrum near simultaneously. So what's the history of this? So this was actually kind of thought up and designed and built as part of a collaboration between the guys at University of Glasgow and Gatan, like back in 2008. So the technology's been around for quite some time. And after this kind of pioneering work by Alan Craven and the Glasgow group, that was actually commercialized in the GIF Quantum, our spectrometer that was released in 2010. Okay, so been around for a while. This is pretty established technology now. So what are the main features of dual EELS? So we'll start off with the GIF Quantum generation, because that was when the feature existed first, right? So Quantum has aberration correction automated to fifth order, 2000 eV spectral field of view at 200 kV, and then you essentially double that when you do dual EELS, because you can offset one spectrum with respect to the other by 2 keV, so effective 4000 eV range. Fast drift tube switching, so 1 kilohertz and approximately 1,000 spectra per second. So pretty fast, okay? And then you've got this 1 microsecond electrostatic shutter, and it's this shutter that allows you to do that very, very kind of tight beam attenuation. And this is what allows us to kind of access the low loss, because we can do this very, very kind of short pulse of illumination on the camera. How do things change with the continuum? So the spectral field of view was increased significantly. So 3000 EV spectral field of view at 200 kV instead of 2000. So like a 1.5x increase. Much, much faster drift tube switching, so 10 kilohertz, and a 10x increase in the shutter speed, okay? So more attenuation, faster switching. And this is really done to support like the faster cameras that exist today. So the spectral rate with Continuum is like 9,000 spectra per second instead of 1,000 that the Quantum supports. There's also a bunch of electron-optical improvements, so symmetrical slit closure, a full-length drift tube, which has some focusing benefits, electrostatic lens that does dynamic refocusing, improved fiber coupling in the fiber couple camera, and then the 2 counting cameras, okay? So lots and lots of upgrades and improvements in Continuum. So the Stellar hybrid pixel thresholding counting camera, and then K3, which is going to be the bulk of the rest of the talk. So high-end counting cameras, faster and better optics is the main take home. Okay, so talking about dual EELS, so let's take a step back. So dual EELS, okay, so we've got 2 spectral ranges that we can acquire, a low and a high. So the question is, like, this sounds wonderful, like dual EELS is great. So why not acquire more than 2? Like 2 is good, like let's acquire like 3, 4, 5, 6, who knows? Okay, so should we acquire more? So it's worth kind of coming back to this slide and then thinking about these 2 bullets in particular. So remember, in an ideal world, our EELS detector would allow us to capture the full spectrum in one go. And acquiring 2 is a compromise, okay? So we want 1, we have to acquire 2 because the detector makes us acquire 2. So if 2 is already a compromise, what reasons are there to acquire more than 2? Okay, so now kind of the remaining slides, we're going to step through some data and some examples. So first of which is dysprosium scan data, so some EELS data from DSO. This is actually a really, really nice system for demonstration and testing. There's a few kind of benefits that we have. So it's basically extremely radiation hard. So it withstands a very high probe current. It's kind of easy to work with. And the sample lasts a long time. Also has a very large lattice spacing, so it's pretty easy to do atomic resolution analysis. So I was quite surprised with this result. This was actually done in our Joel F200 with a very low spot number. So usually when we do atomic resolution on our microscope, we're looking at spot 8, spot 7. But with this like really high current spot number, it's still possible to do this atomic resolution kind of imaging and mapping. There are like kind of nice edges to work with. So the scandium L edge is at 400 EV, dysprosium M at 1295. They're relatively easy to map because they are at low-ish energy loss. Okay, so yeah, good sample to work with. But the primary thing when we're kind of interested in this particular bullet, like single versus many, is kind of like electron optics. And both of these edges are actually really great to characterize like optics because they have really rich LNES. So they have nice multiplet peaks, which you'll see on the next slide, which allows us to kind of see how well or badly aligned our system is. Okay, so what do we have? We have the scandium L edge. So this is just some data from our F200 in Pleasanton, different camera lengths on our microscope, and just, yeah, really, really nice multiplet peaks on that scandium L23 edge. Nice fine structure in the oxygen K. Again, like same 3 camera lengths. And then even if we go out to dysprosium, we still see some nice multiplet peaks on our dysprosium M45 edge. So we have like three target ionization edges in this material that we're interested in. And we need to kind of decide, what do we do? Okay, so should we acquire our data in one range or multiple ranges? So let's start with multiple range. So why would we do this? Okay, so one thing that optics is easier. So if we can change, multiple ranges, we can in principle change the electron optical alignment for each of those ranges. That is inherently more flexible and therefore just easier. We can have 3 different alignments instead of 1. Coming back to the detector, so multiple range is generally going to be necessary for a poor point spread detector. So we'll touch on this a little bit more in future slides. But essentially, using like an indirect camera like a CCD, if you work over a large energy loss range, you'd have low resolution. So, if you want high spectral resolution, you're going to have to use a high dispersion and multiple ranges. Disadvantages, so it takes longer, more readouts is more time. And it's also dose inefficient because we are segmenting the spectrum into kind of multiple readouts and not getting the thing all at once. Single range. So this is more challenging optically. Everything in the spectrum has to be in focus at the same time. So that is more difficult, but can be possible. And this is only going to work with a sharp point spread detector if we want large energy range. So K3 is a really good example of that kind of detector. So we get high energy resolution and simultaneous large energy range. Okay, so if we kind of just zoom in on these bullet points, this one is really kind of the one that jumps out the most. So when we have to do like multi-range, it's essentially we're kind of forced down that path if we have a low resolution or a poor point spread function detector. So it's not necessarily something that we would like choose to do. It's more like the detector is forcing us kind of down that route. So this data is actually single range K3 data. So if the system is well aligned, well set up, this is what you're going to get. So this is my spectrum or my 3 spectra from DSO. And so what you were looking at were just actually subregions of this bigger spectrum. So 1, 2, 3, scandium L, oxygen K, and dysprosium M45. So, one spectral range, everything is really nicely in focus if the system is set up properly, which is really great. And this is with the K3, the HD flavor of the K3. So 57, 60 channels, and the multiple ranges are not required because we have the sharp point spread function and a large number of small pixels. So how is this achieved? So one thing is the optics. So the optics needs to be well set up. The other thing is the detector itself. So it's kind of a characteristic of the camera that's allowing us to do this. So on to the next slide. Detector technology. So K3 direct detection technology. So the K3 is a counting monolithic direct detector. So essentially that means it's a very thin transmission sensor. The counting is done like at the pixel level, and direct single electron counting, and the pixels are small, right? So there's near zero readout noise. This means you can always go at maximum speed. So for the K3 in EELS mode, that's 340 microseconds, give or take, per read. And then this is the really important thing when we're considering our EELS energy resolution. So this type of camera has minimal point spread, and that's because of the transmission sensor and the direct detection. So if you look at this little figure here on the left, the important thing is that this kind of blue, this is like essentially a simulation of the electron path as it goes through the sensor. Basically, this scattering path is really, really small. So the interaction volume in the sensor is tiny. And that's sharp point spread. If we compare that to a traditional fiber coupled camera, the picture here is quite different. So you have a scintillator, which is bonded to a fiber optic stack, which is then bonded to CMOS, CCD, or a linear diode sensor, right? So the electrons come in, generate photons in the fiber optic, and then you have this massive kind of decay path in the fiber optic glass, right? These guys have finite read noise, so typically you need to run these at a longer exposure time to kind of offset the readout noise. But the resolution hit that we're paying here is this point spread, so significant point spread due to this indirect detection pathway, right? So that is this blue kind of cascade of interaction in the glass. So that's the theory. And what does it look like in practice? So the effect of point spread on energy resolution in our data, right? So CCD has poor point spread, so it's a high point spread. That means at large energy field of view, we're going to get relatively poor energy resolution. So the point spread function typically is going to be 3 to 5 channels for a fiber coupled camera. What does that mean in real money? So it means that for a 2K detector running at 1 EV per channel, we're going to get a 2000 EV energy range, but the price that we're going to pay is that the energy resolution is going to be 4 EV, give or take. Okay. Now, with a K3 in HD format, we have a large number of pixels. So 5760 energy loss channels in one spectrum. Plus, it has a very low point spread, very sharp point spread. So we get large energy field of view and high energy resolution at the same time. So that's quite a win, okay? So if we kind of think, you know, you could assume that if you wanted to do something at high energy resolution, you need to work at high dispersion. So maybe we need to do 0.1 EV per channel to get our source resolution from a cold FEG. So 0.1 EV per channel, we get a 0.4 EV full width path maximum, okay? So figure of merit for our energy resolution. That gives us, you know, it's not too bad, 576 EV range, but this would limit us from many experiments. So let's decrease the magnification and see what happens. So 0.35 EV per channel. So then look, because we have this sharp point spread, our full width path maximum is a single channel, so 0.35 EV full width path max. And now we have a 2000-ish EV energy range. Go even further, and 0.53 EV per channel dispersion. So this is our lowest dispersion. Again, we've got a single channel full width path maximum, 3052 EV range. So this is very compelling for core loss analysis and any EELS experiment, right? So the HD format K3 is giving us near cold FEG resolution. So this one in the middle, with simultaneous like energy range per spectrum, which is more than 2000 EV. So that's like very kind of a strong characteristic of the camera. So what does that allow us to do? So this is strontium titanate, that 0.35 EV dispersion. So we've got this 5760 channels, 2016 EV energy range. So what you're looking at here is a single spectral range. So it's many frames summed, but it's one electron optical range. And we have our titanium L edge and our strontium L edge in the field of view of this single spectrum. But if we zoom in, you can see that we have nice kind of energy resolution. So we can see our multiple peaks on the titanium L edge. We can see our oxygen K fine structure nicely. We can see nice sharp white lines in the higher energy L edge, so the strontium L edge. And the SNR is like great because it's a counting camera. Okay, so why is it important to do this quickly? Well, I'll come on to that in a little second, but you can take a guess. Going fast allows you to do things at higher spatial resolution, better drift correction. So we were able to do atomic resolution mapping on our F200s with this setup. So yeah, I kind of jumped ahead. So the question is, what does this acquisition strategy buy me in real world experiments? And yeah, it buys you quite a lot. Okay, so EELS spectrum imaging, speed is important. So there's kind of two acquisition strategies that we might consider here. So spectrum imaging with a counting camera, because we don't have readout noise or near zero readout noise, you can always run as fast as possible. So with the K3, that is 339 microseconds. With fiber coupled or indirect technology, essentially you want to maximize the signal per read to get above the noise floor. So we minimize the number of times we read that camera, and typically you'll run at slower, right? So something like 10 milliseconds is probably not unreasonable for a total acquisition time, okay? That's going to give us enough SNR for the data. And this is probably with a high current as well, with this kind of camera, okay? So these are the differences, right? Hundreds of microseconds versus, tens of milliseconds. So this, this might seem quick in isolation, but you should compare this with the sort of frame rates that you get from modern high-speed cameras. This is a very slow number. Okay, so if we go back to the DSO, like why is that important? So what you're looking at here on the left is data that is acquired at near 100 FPS, so a single pass, versus 3,000 spectra per second on the right. And you can clearly see that there are like scan distortions and artifacts in the data on the left that are not present in this like high speed, like dose fractionated acquisition on the right, okay? And this is an example of a fairly easy, robust sample that behaves quite well in the microscope. So even with something that's straightforward, we have an improved outcome using the counting camera to go at high speed. So we have rigid frames, like much nicer images on the right. And when those are summed up, you end up with a result that is kind of superior to this kind of slow scanning on the left. How about something that's actually challenging? Okay, so here's a nice example of strontium ruthenate on dysprosium scandate. So this one is interesting because this is actually something that's beam sensitive on something that's radiation hard. So you can look simultaneously at something that is beam sensitive and something that is beam indestructible, basically. And there was a material science angle to this. We're interested in kind of the ruthenate, like kind of the damage characteristics of the ruthenate. But it's also interesting to see can we do atomic resolution mapping in this sample, and why is this more challenging? Okay, so we're actually trying to do this at liquid nitrogen temperature because this is like beam sensitive, and we're trying to mitigate the damage through cooling. So the bigger project is actually, does the cooling reduce the damage in this material? But it's also a good kind of measure of how does a counting camera behave, like fast versus slow. So if anyone's particularly interested in this, okay, so this was actually reported in more detail in the previous webinar, like a few weeks ago, about dose fractionation. And the QR code will link you to that example. And yeah, so just to show you that this was a real experiment. So here's just an iPhone video, cooling holder, and yeah, there's my cryo experiment. And you can see that there's atomic resolution information, nice kind of rigid frames in the ADF. And just before I move on, kind of a big thank you to Berit Googe. So this was one of Berit's samples, and the project would not have proceeded without this sample. So thanks very much for collaborating on this one. Okay, so we're talking about, drift, fast versus slow. So next slide is just that. Okay, so we have this video here. So this is actually 100 microsecond data on the left, so multi-frame, versus 10 milliseconds on the right. And this is to show you the difference when the sample is challenging. So if we go at a higher speed, okay, yeah, there we go. Okay, so the left data, very, very fast multipass scanning, and the data on the right is a single pass with row-based drift correction. And the important thing here is that data on the left has like rigid frames. Like there is some kind of wobbling around, but that can be removed post-acquisition. This data on the right has kind of irreparable artifacts in here. Okay, the scanning is not fast enough. There's these weird discontinuities where the drift correction is stopping and starting, and there's really like no atomic resolution in this data on the right at all. Okay, so in this case, the slow readout is really kind of giving us catastrophic resolution loss. So the speed is important. If this isn't done fast, this experiment will fail. It will just not work. Okay, so it needs to be done at high speed, needs dose fractionation, needs to be done ideally with a K3 camera. So what did the results look like? Okay, so that was just kind of the videos of the thing happening, and this is the kind of the end result. So the take home here is dose is also important. So speed is important because we want to mitigate that drift, but dose is important. Like this sample is beam sensitive, so we need to get our data with making every electron count. So it's generally desirable to use the minimum dose possible to get the result you need. Now that's true of things that are beam sensitive. It's true of like most samples, right? If you can get your data more efficiently in less time, it's actually more efficient on the microscope. You can run more samples. It's kind of more like time efficient. It's more cost efficient. So just to show you like kind of an interesting result here, again, this was in the previous webinar, but this is single counted frames, kind of multi-pass. This is just showing you one pass. And then this is the end result if we sum all of those fast individual pixels up. So it looks like it's not going to amount to anything, but because of the high sensitivity and high speed of the counting camera, you basically can get this really, really beautiful atomic resolution data under cryo conditions. So challenging conditions, low probe current, and we can do imaging and EELS mapping even at high energy loss, right? So this is ruthenium L here is at 2800 EV. So this is not a low energy loss signal. And this was done at 20 picoamps, and the individual pixels are a few hundred microseconds. But remember, like all of these guys are in one spectrum. So, that's why we can do this. Like these are all in a single spectrum. They're not in like many, many spectra. So make every electron count, go as fast as possible, ideally. What next? Okay, so this is our final example and just kind of something I wanted to show that is a nice semiconductor device. So it's a FinFET chip fib section that was kindly prepared for us by an external collaborator. So what are we doing here? So this is showing you the K3 HD kind of setup again in dual EELS. So from our F200 70 picoamp probe. And what I'm doing is mapping over this kind of sub-region that you see in green. Okay, so over here on this kind of figure on the top left. And just to show you, yeah, the resolution here is pretty sharp. So I have my single channel full width half maximum, 0.35 EV is that full width half max, 2000 EV range. Now, why is that important for us? So this sample has a large number of elements over a wide energy loss range. So we need to do mapping, but we also would like to do EELS mapping. So we kind of want to have resolution. We also want range, okay? So what we're looking at here now at the bottom is a spectrum that is summed from this kind of blue subregion here that I've just annotated on that image. And this is just to kind of, as an example, to just show you like kind of what is in this spectrum. So we've got our lowest energy feature is the silicon L edge. Highest energy is probably our silicon K. But what's cool is these guys are in this one spectral range. So, you know, one range, we get everything. And then I've had to boost the scale here just so you can see it. So this discontinuity that you see in the middle of the spectrum is like a post-acquisition modification that I've done. The spectrum doesn't actually do that in reality. Okay, so I said we're interested in mapping. Let's walk through the data. So what do we have? Okay, so a zoom in of our spectrum image ROI, and that's the area that I was particularly interested in. So sample this area, 0.8 nanometer pixels, so pretty high spatial resolution. And this, just before I move on, this was another dose fractionation example. So each one of these spectrum image frames was acquired in 30 seconds, but I acquired like many of them with continuous scanning and continuous drift correction. So this is kind of important. If the sample is like not stabilized, acquiring like this would allow us to get data without having to wait for, you know, spatial stabilization of the sample. So that's kind of a nice way to acquire the data, even if we're not doing something complicated like cryo-atomic EELS mapping, okay? This acquisition strategy is generally always preferable. Right, back to the EELS. So what do we have first? So we have the silicon L edge. So I just pulled out what looked like 5 spectral fingerprints for the silicon L. So pink, purple, blue, red, and green, we'll call them for now. I haven't done a deep analysis of what these chemical phases actually are, but it looks like there are 5 phases. We can see those phases because we have decent energy resolution in the spectrum. And what can we then do? So we can use these as fingerprints to do linear least squares fitting or mapping. So we can get this nice composite map showing kind of the spatial distribution of these different silicon phases. So the color scheme that you see on the right here essentially matches what you see on the left. So pink, purple, blue, red, and green flavors of silicon. What next? So we've got our silicon map, our ADF, and we can just keep going through the spectrum. So we also have nitrogen, and we have enough energy resolution that we can pick out 2 distinct nitrogen phases. So nitrogen red, nitrogen green, okay? So we have an RGB composite of our nitrogen. We can do titanium L mapping again. So gonna just walk through the spectrum. Oxygen, so 2 distinct oxygen fingerprints. And we can just keep on going, okay? So nickel, nickel L. So we have some nickel regions, germanium, aluminium, so aluminium K, and tantalum. So we can map the tantalum M edge. And there is silicon K, but the silicon K mapping is actually a little complex in this sample because of overlap with the tantalum mainly. So I decided not to do the silicon K mapping, but it would be in principle possible. Okay, so this is what we have with the K3 HD. Okay, so our 5760 channel, like 2016 EV range. So all of this stuff is just extracted regions from my like kind of one large spectral range. So if this was done in multiple ranges with a 2K CCD, how many ranges would we need, okay, if we're targeting cold FEG resolution? So the 2K detector at 0.1 EV per channel is going to give us 200 EV range with 0.4 EV resolution, right? So point spread of, like, say, 4 channels, so it's 4 times 0.1. That's how we get this number, right? 200 EV range. So we're going to use 1 for our zero loss peak and our low loss. 2 if we want the silicon L, so we can comfortably do our silicon L edge in another one. Now we could do nitrogen, titanium, oxygen, but we're likely going to crop the oxygen if we have a setup like this. Okay, so that's why I've written oxygen partial. This is arguably also probably too small a background window for the nitrogen, but you know, I'm going to be optimistic and hopefully it would be okay. We need then a 4th one, right? Because we don't really want to crop the oxygen, so we need oxygen separately. Nickel L, okay, so a 5th one. Germanium, so germanium I've labeled as partial because I'd say that crops the germanium slightly. And then this is going to become like an ongoing problem with the things that are at higher energy loss, because those ionization edges are kind of spread out over a larger energy loss range. So we get like most of the aluminium K edge, but it's like, do we get everything? And then it's the same for the tantalum. We definitely crop the tantalum. And the silicon K, okay, is also probably partial, right? So we're up to 9 ranges that we need to do the equivalent acquisition with a 2K CCD. So that is more than I'm aware is possible with, you know, things that we've seen. So nine is a lot. So maybe a better way to do that would be to run at a lower dispersion and have like less of those ranges, but then you're going to be trading resolution. So take home there is that you can't really have resolution and the range. Even with this kind of, even with like multiple ranges, you're going to struggle. But with the K3 HD in particular, we can do this whole range at near Colfeg resolution in just one like kind of optical setup. So one spectral range gives us all of this core loss. We are going to do dual EELS if we want the low loss, right? So this is dual EELS data, but that's just 2, okay? So we've got 1 for our zero loss peak and low loss, and then 1 for all of the high loss, right? And it's done at high speed, dose efficient with high speed drift correction. So, you know, a much more preferable setup. Okay, so that's actually the final example. And yeah, so I'll just end on this summary slide. And yeah, summary, less is more. So the sharp point spread function and large format of the K3 gives us a very large energy range at higher energy resolution in every spectrum that we're going to require. So if we break the spectrum into multiple EELS ranges, that's going to increase the dose and therefore damage for each one, basically each complete spectrum, because you're overdosing the specimen. Increases the time required for each complete spectrum, because we have to do, you know, many things instead of one. And this really stops us doing dose fractionation and in situ. Like these two things are very, very similar kind of setup. All right, dose fractionation and in situ. These need to be done at high speed and with very short spectrum image pixel times. So ideally single frames from the camera. As soon as you start adding frames and making your SI pixel time long, this whole thing doesn't work anymore, just falls apart. The final bullet, collecting core loss EELS data in a single K3 spectra readout is probably the most dose efficient means to detect data at optimized spectral magnification. So we don't have to over magnify with the K3. We can work at like the lowest magnification possible to give us the like sharp energy resolution data that we want. Okay, so that is the end. So thanks everyone for attending. I talked for quite a while. And just on this final slide, I've just added a few QR codes if anyone wants to take a snapshot. So just kind of wheeling around here, we've got the e-brief that Andrew wrote with the transition metal K-edge mapping, the cryo dose fractionation webinar. And then if anybody is attending either of these two conferences, so M&M 2025 or MMC 2025, I'll be at both of those conferences, and it would be lovely to see people in person to talk about any of these things, or yeah, like, because I'm presenting essentially that cryo data at MMC and M&M, but we'll also be at the Gatan booth like throughout both of those weeks. So thanks everyone for attending, and that's probably a good point to break off for questions if there are any.
Hey Liam, good job. This is Andrew. A lot of great data there. One of the questions was how do you do the post-acquisition drift alignment? Are you doing everything by hand, or is that something that's automated?
That's actually, I mean, there are some user, it's automated with some input that you have to give. So essentially what you do is you measure a drift profile from the data, and the software will then output the drift profile, and you then decide whether to apply that drift profile to the data. So typically what I would do is I usually measure the ADF data because it's the highest SNR, and it's also easiest because it's the smallest data set, and then apply it to the rest of the spectrum imaging data sets. So there's a few things that you can choose to do, like you can choose like filters to run and like kind of sub regions to do the analysis on, but the actual bulk of it is essentially automated with some user defined settings that you have access to. It's pretty straightforward, and it's also very quick.
And there's also a bunch of image filters you can play around with that maybe some will work best for certain types of samples than others, huh?
Yeah, so actually it's kind of on my to-do list to prepare a tutorial to show like how to do that. So that's something that we probably, you know, pay attention to the kind of the social media feeds and the website, and we'll try and put a tutorial up soon. Or if anyone's coming to either of these conferences, I'd be happy to show you on like real data, like one-on-one at the shows.
Nice. Yeah, I think we get a lot of questions about that from people, from customers.
Okay. Fantastic.
The other question was so you mentioned that you did MLS fitting for the silicon and the oxygen maps. Was that just MLS fitting, or what was it? Did you use that in the quant tool?
So I actually did them differently. So this one is using the linear least squares tool. So what you see here is just the fit coefficients, and that was just more of a time-saving exercise. It was just easier at the point that I was looking at this data. And I also I'm not, you know, I hadn't fully decided like how many phases there were in the sample. So that tool is actually nice and easy to work with because it gives you this like live fit. So it's quite fast to use. Now everything else is actually using standards-based EELS. Okay, so that's linear least squares fitting, but it's within the actual elemental analysis. So the elemental quantification tool. So that's why we have areal densities here. So I did standards-based fitting with concurrent standards. So 2 different standards for nitrogen, and then 2 different standards for oxygen. Yeah, so that's I use both. Okay, so I use the quantification with concurrent standards for oxygen and nitrogen, but I just use the more generalized linear least squares tool for silicon L. But I think when I have more time, I'll probably go back at this and spend a bit more time on the silicon L maps and probably use the quantification tool because I prefer having areal density maps. Yeah, good question.
Yeah, it makes the data set a lot richer, huh? Because you're not just looking at where the silicon is at, you're actually seeing phase changes.
And that yeah, definitely. If you just map the silicon here, it would just all look the same, right? There's silicon everywhere. But there are
it's a blue or something, yeah.
5 phases. And yeah, this has like probably functional impact on the device, like the thickness of these layers, whether they have any discontinuities or like kind of breaks in them and so forth. So it's kind of important to do this kind of mapping. And also to be able to do it like fast and efficiently. If you need to look at like a large number of these samples, you don't want this to take forever, right? You want to be able to just do it, trust the result, and move on. So
right.
It's nice to be able to acquire the data quickly, but then also process and analyze it quickly without having to go off somewhere. Because you can do this like while you're at the microscope. It's really not computationally challenging. It's very fast.
Nice. I think that was it in terms of questions.
Okay, great. I'll go back to the others. Well, okay. So if there are no more questions, I'd like to thank everyone for attending again, and thanks Gatan team for supporting internally. And I guess it would be great to see people at those shows if anyone's attended. So see you soon, either in person or at our next webinar when it comes.